Hello everyone, I am Yidan Wang from the Chinese University of Hong Kong, Shenzhen. I am a master in my second year. This paper was co-authored by Zhuzhou Ruixing, Fu Qiuai, Ma Yuchi, and He Pingjia. Today, I will be presenting our paper, MRCA, Metric Level Root Cause Analysis for Microservices via Multi-Modal Data. The presentation will be introduced by 4 parts, include introduction and motivation, methodology, results, and conclusion. Let us enter the first part, introduction and motivation. This figure is an anomaly propagation chain in a microservices system. The anomaly may be caused by train service, which is the red node in this graph, and spread to basic, passive, and front-end services. We need to implement anomaly detection. It allows us to identify when anomaly happens in this system. However, we often need finer-grained information, such as which service caused this anomaly, which can help SREs to repeatedly solve it. So we need root cause localization. This process helps us pinpoint which service in our system is more likely causing the issue. If the anomaly is detected, the root cause localization process begins, aiming to identify the failing service. This whole process is called root cause analysis, also called MRCA. However, some alarms may be false, and some anomalies may not be detected, so we need more accurate anomaly detection. Just like this figure, the cause in this system is very complex, and Alibaba Cloud is large-scale. Manual RCA is a large workload task. Amazon's 1-hour downtime resulted in a loss of up to 100 million. These incidents indicate the necessity for efficient and automatic root cause analysis to minimize downtime and ensure the reliability of services. We will introduce the trace data. This figure helps us understand the single request through our system, and the trace contains a call graph like this figure. Each call has unique span ID, and the same request have same trace ID. There is processing time when A calls B, such as sending a request and waiting for a response, and so on, which is called duration. So we conclude the existing model's limitations, which include insufficient data exploitation, ignoring the importance of anomaly detection stage, low efficiency or coarse-grained. So we need to solve those limitations. How can we achieve those? Let us enter the methodology part to explain. The first step is data processing. We classify logs and traces according to different services, and the data format is as shown in this figure. We implement GUI to extract different templates of logs, and we record the number of different templates. We also record the duration contained in trace. Finally, we aggregate them by time step. Then we perform anomaly detection. We use normal data to train VAE. Net VAE learns the distribution of normal data. Online data is input into the trained VAE for reconstruction. If the probability of reconstruction is lower than a threshold and the data distribution is significantly different from the normal state, it is judged as abnormal. Continue to calculate the abnormal score based on it and rank the abnormal services. Otherwise, the system is normal. In this figure, the most likely cause of the fault is services M, and the second is services N. Further combine metric data to build servicing metric pairs and construct causal graphs. The causal exercise method the paper uses is Granger, which was relationship between service VI and VG. Let's us guess it. Okay, by exercise, we can get the results of VI leading to VG. What's more, the cause occurs earlier than the result, so VI is more likely to be the root cause, which is also the basis for subsequent pruning. Then we implement reinforcement learning. The initial node is A and nodes E, F, and G are potential expansion nodes of the graph. Each possible action expanding to a certain node or ending has a corresponding Q-value. We should select the action with the highest Q-value. In this example, action 3 is selected because it has the highest Q-value. So node G is added to the causal graph, and we calculate the reward. The reward is determined by the complexity of the graph and the accuracy of results. The higher complexity, the lower reward. The higher accuracy, the higher reward. So the alpha is negative, the beta is positive. By this way, we can achieve lower complexity and higher accuracy. Then reconclude the Q-value and iterate this property until the Q-value of the termination action is the highest. Finally, we prune the causal graph and get the result. As we discussed before, the more likely root causes don't have parent nodes, just as the node email CPU, cart latency, cart CPU, payment latency. So the red nodes are the nodes retained after pruning, and then we get the final rank list. Just like the email CPU issue, payment latency issue. The result part. The performance comparison for anomaly detection is shown. MRCA significantly outperforms other methods, indicating that it has fewer missed anomalies and further errors, and a more accurate anomaly detection process its subsequent cause location. Comparison of approaches at metric level, utilizing multimodal data, thereby allowing for more comprehensive understanding of the system and accurate root cause localization. The efficiency comparison. MRCA provides the abnormal services list on AD stage, which reduces the RCL's processing time. What's more, pruning and timely termination of the expansion of the causal graph can improve efficiency. Conclusion part. MRCA enhances both speed and precision in root cause analysis by implementing reinforcement learning and multimodal data. The approach provides fine-grained metric-level root causes, aiding quick resolution of anomalies in microservices. Thanks for your listening, and I'm actively looking for PhD positions in LM for SE.